All right, the drawing below, no, the drawing on the left represents a buffer. Drawing on the left, this drawing. Represents a buffer composed of equal concentrations of weak acid and its conjugate base. The heights of the column are proportional to the concentrations of the components of the buffer. A. Which of the three drawings, 1, 2, or 3, represents the buffer after the addition of strong acid? Okay, so A. We're dealing with this system, right? Weak acid breaking apart to form H plus ion and its conjugate base. So if I put a bunch of strong acid in here, that's going to shift the equilibrium back towards the weak acid and lower the concentration of the conjugate base. So we're talking about drawing 3 as representing once we've added strong acid, right? Strong acid will, as the H plus concentration increases, so does the weak acid concentration, and the conjugate base concentration goes down. And we shift the buffer this way. All right, so B. Which of the three represents the buffer after the addition of strong base? All right, so if we add hydroxide to this system, we're going to drive the equilibrium this way by eating up this H plus ion, all right, forming water. So as I drive it in this direction, I'm going to lower the weak acid concentration and raise the conjugate base concentration until I get to drawing 1. All right, and now we shifted the equilibrium to where we have more conjugate base than weak acid. C. Which of the following three represents a situation that cannot arise from the addition of either weak acid, or either adding H plus ion, acid, or hydroxide, base? The answer to this is 2. You can't lower both the weak acid concentration and the conjugate base concentration by this way, right? As one goes down, the other's got to go up as we add hydroxide or add H plus ion. The following drawings represent a solution at various stages of the titration of a weak acid with hydroxide. Sodium ions and water molecules have been omitted for clarity. All right, so we've left out that spectator ion and water. Which of the following regions of the titration curve does each drawing correspond? A, after the addition of sodium hydroxide. All right, so I added an extra drawing here. I added a titration curve. All right, this is a weak acid being titrated with hydroxide. So at the beginning of this, before I've added any hydroxide to this, we have all weak acid. All right, so that's drawing 3. So we're starting down here at the beginning of this reaction, right? It's all weak acid. So let's say we had 1, 2, 3, 4, 5, 6, right? Weak acids, right? 6 molar concentration. It's about the ionization of this weak acid in terms of what the pH would be at the beginning of this reaction. So this would be a Ka problem, right? Weak acid breaking up to form H plus ion and conjugate base. All right, B, after the addition of sodium hydroxide but before the equivalence point. All right, so as I start adding hydroxide to this, I start eating up that weak acid and start forming conjugate base, right? The green ball without the H attached. So we're looking at drawing 1 here. So the weak acid concentration is going down, the conjugate base concentration is going up. So as I add, say, right, so we went down to 2 moles of weak acid, so I would have had to have added 4 moles of hydroxide to eat up 4 of those moles of HA to bring it down to 2. And that would mean I'd make 4 of the green balls, right? 4 of the conjugate base. So at this point, we have a buffer, right? If I want to solve for the pH at this point, I can plug moles of the weak acid and conjugate base into the Hasselbalch equation and solve for the pH at this point, right? Notice we have a flat curve on a flat spot on my titration curve. All right, so we're going towards the equivalence point, so the pH isn't changing very much because of that conjugate base in there eating up all the weak acid, all the H plus ion that's being added. I'm sorry, I take it back now. We have weak acid in there adding up all the hydroxide that's being added. All right, C, at the equivalence point. So at the equivalence point, we have the big jump, all right, the big jump in pH, because at this point we've burned up all the weak acid. The weak acid's gone, right? We have equal amounts of hydroxide and equal amounts of weak acid. So if I added 6 moles of hydroxide to my 6 moles of HA that were in there originally, I'd have no more weak acid and only conjugate base. So at this point, it's the conjugate base that's affecting the pH. So notice the pH of this weak acid is about a pH of 8. That's because of the hydrolysis of that conjugate base with water to form hydroxide. So when I'm titrating hydroxide with a weak acid, the conjugate base is affecting the pH at the equivalence point, and the pH is above 7. And D, after the equivalence point. After the equivalence point, all that's left is excess hydroxide. All right, so, or I should say, that's not the only thing in there, right? You've got conjugate base, but the main thing affecting the pH is the leftover hydroxide. So I'd have to look at moles of hydroxide that were left over after the equivalence point, divided by whatever the volume is at this point. It's an imaginary titration, so we'd get the concentration by having my 2 moles of leftover hydroxide divided by the total volume of the solution. And I'd get the hydroxide concentration. I could get the pOH, subtract from the pH, subtract from the pKw, 14, to get the pH at this point. Match the following descriptions of titration curves with the diagrams. A strong acid added to a strong base. All right, so if you're adding to a strong base, you're starting at a high pH, going to a lower pH. So this would be diagram 2. Strong base being added to a weak acid. For being added to a weak acid, we're starting at a low pH, but not as low as you would for a strong acid. Something above, 1. And this would look like diagram 3. C, a strong base being added to a strong acid. Okay, so we're starting down at a lower pH, and you'd have an equivalence point close to 7. Also, you get a very symmetrical looking curve with a strong acid being added to a strong base. And D, a strong base added to a polyprotic acid, right? An acid that has multiple H's. So that means several humps, right? The first equivalence point losing the first H, and the second equivalence point losing the second H. Equal volumes of 2 acids are titrated with 0.1 molar sodium hydroxide, resulting in 2 titration curves in figure A. Which curve corresponds to the more concentrated acid solution? Well, the more concentrated the acid solution, the lower the pH. So the red curve represents the stronger acid. Which corresponds to the acid with the larger Ka? Explain. Well, the larger the equilibrium constant, the more spontaneous the reaction, the more acid ionization occurring. So again, the red line. You're starting at a lower pH, so this acid has ionized more. You've got higher concentration of H plus ions. Saturated solution of cadmium hydroxide shown in the middle beaker. If hydrochloric acid is added, the solubility of cadmium hydroxide will increase, causing additional solid to dissolve. Which of the 2 choices, beaker A or B, accurately represents the solution after equilibrium has been reestablished? Explain. Chloride ions and water have been omitted for clarity. All right, so cadmium hydroxide is an insoluble solid, yet there is some equilibrium between the cadmium ions, the yellow ones, and the hydroxide ions, the red, white ones. So if I add acid to this, it's going to pull the hydroxide out of this equilibrium. The system is going to respond to try to replace it. So I'm going to drive it towards beaker A. So adding H plus to this pulls hydroxide out of this. It lowers the OH concentration. The system responds to try to replace it, which will raise the cadmium ion concentration. Again, driving this reaction forwards. So as the hydroxide concentration goes down, the cadmium 2 plus concentration goes up.